Hello, CE93 students. The topic of today's lecture is bivariate regression. Here is what we're going to be talking about. First, I'll introduce the topic, and then we will learn how to estimate bivariate regression models using the method of ordinary least squares. We'll see that although these are linear models, the same techniques can be used if we're clever to estimate models that are nonlinear. In addition to learning about how to get the estimates for these models, we will learn about the properties of those estimates, properties of ordinary least squares estimators. That will lead us to the confidence intervals for these estimators. The result of a ordinary least squares model includes something called the coefficient of determination, and we'll learn about that. And finally, we'll learn how to examine the residuals that we get in an ordinary least squares model in order to determine whether the data is well behaved for the kind of model that we're estimating. So what do we mean by bivariate linear regression? Bivariate means two variables, and here they are. The variable we typically call y is on the left-hand side of a regression model, and it is related to the other variable, which is called x. Y is known as the dependent variable, x is known as the independent variable, and the relation between y and x includes an intercept, a slope, and in addition, in our model, there is a random term which gives the difference between a particular observed value for y and the predicted value based on our model. Because the error term is random, so is the dependent variable y. If we draw a picture of this kind of model, we see that down here. Here are our individual data points, and we use those data points to estimate the values for the intercept and for the slope, and we recognize that the model, the line defined by the intercept and the slope, does not perfectly predict our y variables. The difference between the actual values for y, given by the blue dots, and the predicted value based on the model is known as the residual. And we see that in the context of this plot, it's the vertical distance between a particular data point and the linear regression line. So that's what we're trying to work with today. And so as far as using data to get our values, our estimates for the slope and for the intercept, we have to start with what the observations are. So we're going to have a set of paired observations. The first observation will have values for x and y, and then a second observation will have another pair of values for x and y respectively, all the way up to n observations. And our goal when we are using ordinary least squares to estimate this model is to minimize the squared difference between the observed values for y in our data and the predicted value for y based on our intercept and our slope. So over all the observations in our data set, we calculate the difference between the observed y and the predicted y, and then we square it. It turns out that the solution to this problem, in other words, the values for beta 0 and beta 1 that solve this minimization problem are given by the expressions below here. So beta 1, and here we call it beta 1 hat because it's an estimate for the true value of beta 1, which we don't know, is going to be equal to the sum over all the observations of the product of the difference in that observation between the x value and the mean of x and the y value and the mean of y, divided by the sum over all the observations of the squared difference between each individual x and the mean of x. So this first expression gives us our estimate for beta 1. Beta 0, the intercept, is obtained easily once we've gotten beta 1. We say that beta 0 is beta 0 hat is going to be equal to a y bar, the mean of all the y's in our data, minus our estimate for beta 1 hat, times the mean of all the x values in our data. Now, although this kind of model is referred to as a linear regression model, it can actually be used to estimate nonlinear relationships between x and y. What we mean by linear in the context of linear regression is that the model is linear in the parameters, beta 0 and beta 1. That does not mean that the model has to be linear in x. So here are some examples where the model is not linear in x, but through various tricks, we can make it linear in the parameters. The first example, known as a quadratic model, is not really very tricky at all. It is exactly like the original regression model, except we have x squared instead of x in the beta 1 term. And in order to estimate a model like this, we would just take our original data for y and x, take the square of x, and use the square of x in place of the original x in our estimation. Here's a second example known as an exponential model. In this case, the value y depends on e raised to beta 0 plus beta 1x plus our error term. How can we make that into a linear model? Well, if we take the natural log of both sides, the y becomes the natural log of y. And remember, the natural log of the exponent is just the original argument of the exponent, so we get that the log of y is equal to beta 0 plus beta 1x plus epsilon. And to estimate this model, starting with the original data, we would take the y values, take their natural logs, and use them in place of the original y's in the data set and proceed as before. Here's a third example known as a log linear model. In this case, we have that y is equal to e to the beta 0 plus epsilon times x to the beta 1. So the beta 1 appears in the original model as an exponent, and the beta 0 appears in the exponential term. This may look like a rather daunting model, but if we take the log of both sides now, we get the log of y is equal to beta 0 plus beta 1 times the log of x plus epsilon. In this case, we would take the original data, transform it by taking the log of y and the log of x, and proceed as before. Finally, one other example is an inverse model. In the inverse model, we have that y is equal to 1 over a linear function of x, beta 0 plus beta x plus epsilon. And the trick there is to take the original data and transform it by taking the inverse of our y values. So we have this expression, and by using the inverse y values in place of the original y values, we can again estimate a model using the conventional ordinary least squares estimates. Now in these next few slides, I want to give you sort of an intuition about how the residuals introduce randomness into our estimates for the slope and intercept that we get from our OLS formulas. So in this plot, first let's look at the blue line, and there it is. The blue line has 4 points on it, and those points are what we would observe in our data if it weren't for the residuals. So we assume that the model would be perfectly linear and the fit would be perfect between the data and the fitted line were it not for the residuals. Now, when we actually do an estimate, we don't observe the blue diamonds. What we observe instead are the magenta squares. And the magenta squares have the residuals included, and it is the residuals that make them different, to create some vertical displacement between them and the blue diamonds. So based upon the magenta squares, we would estimate a particular regression line, and in this particular case, applying those ordinary least squares formulas for beta 0 and beta 1 we talked about earlier, the green line is the line that we would get, and we see that the green line in this particular case is, of course, different from the blue line. The blue line is what we'd get if it weren't for the residuals. In this particular case, the two lines seem roughly parallel to each other, but what is different is the slope of the, what is different is not the slope, but the intercept of the green line as compared to the intercept of the blue line. Now, since the residuals are random, in another occasion with a different sample, we might, and in fact would, get a different set of residuals. So let's look at another possible set of residuals that we might get. And here it is. So in this plot, the blue line and the blue diamonds are exactly the same as before, but the residuals are different, and we see that as a result of the residuals being different, the green line estimated from the observed data is also different. And in this case, the green line has a somewhat lower slope than the blue line, and it looks like it would have a higher intercept as well. And here's another case. In this case, the green line has a higher slope and a lower intercept than the blue line with this set of residuals. Yet another case. This time it has a lower slope and a higher intercept. And finally, one last case. In this case, it has a higher slope and maybe roughly the same intercept as compared to the blue line. So the point is that in each of these cases, if we applied our formula, our formulas for beta 0 and beta 1, we would get the values implied by the different green lines. And although the underlying relationship is the same as given by the true line, our estimated relationship is going to be different because of those residuals. Now, with the assumptions that we made before about the properties of the residuals, that they're normally distributed, have the same variance, have a mean of 0, and are independent, we can derive the properties of the randomness in the estimated values for the slope and the intercept. And here they are. If with those assumptions about the residuals, it turns out that the slope and intercept estimators will be normally distributed. They'll be unbiased. In other words, the expected value of our estimate for beta 0 is equal to beta 0, and the expected estimate for our slope estimate for our slope value beta 1 is equal to the true slope. And furthermore, that these estimators have variances. The variance for the slope is given by the variance of the residuals divided by the sum of the squared difference between x and the mean of x across all the observations. The variance of the intercept, beta 0 hat, is also going to depend on the variance of the residuals, in this case multiplied by the sum of the x's squared divided by n times the sum over all the observations of the squared difference between each x observation and its mean value. Now, we just saw that the variance in the estimated slope and estimated intercept depends on the variance of the residuals, but typically we're not going to know what that variance is, but as we have in the past lectures in the context of, say, estimating the variance of a sample from a population, we can estimate sigma squared from our data. And the maximum likelihood estimator for sigma squared is going to be equal to 1 over the number of observations times the sum of the squared differences between the observed values for y and the predicted values for y based upon our estimated slope or intercept. This estimator is going to be biased downward, and the unbiased estimator for sigma squared is given by n over n minus 2 times the estimator we just talked about, or plugging that into the formula. This is the unbiased estimator for sigma squared for our bivariate regression model. We can even go further and develop confidence intervals for the sigma squared value. And in this case, we would start with the fact that the number of observations times our estimated value sigma squared, remember, note this is the MLE, not the unbiased estimator, divided by the true value sigma squared has a chi-squared distribution with n minus 2 degrees of freedom.